So yeah, Dimitri, do you want to go through the chat and ask the questions?
Yeah, I mean, first of all, if anybody has any question while we're talking, please feel free to put it in the chat. We're gonna keep a track on this. All right, because I guess like most of the questions is from my side, so I would say that it's good
Yeah,
that more people uh, get some questions to our speakers. Um, I would say probably I would start with Lorenzo Natal is still there. Yes, I can see him. All right. So Lorenzo, are you there? I mean, you can unmute so that I'm sure that I see you, but I don't see you unmuted. All right. Okay. Cool. So maybe I can start the question.
You're afraid I'm recording, so I need to show you something. My watch is
All right.
moving.
Okay, cool. So my first question is, uh, so grasp success on one robot may be a failure on another based on its physical characteristics. So is it the problem of having a generic framework for grasping, or its robot needs to be fine-tuned with its own embodiment, basically? Do you believe that the benchmark based on a particular robot may also be helpful to realize failure grasps to other robotic systems?
Yeah, I think so. Clearly, the different robotic platforms can perform in different ways, and there are robots that may be more appropriate for solving a specific tasks than others. But sharing benchmarks across different robots, I think it's beneficial because you can understand. There might be a benchmark where a particular robotic hardware is performing very well. That is, on the other hand, is very hard for a different robot, and the other way around. So you can definitely learn much more by exchanging benchmarks, because sometimes you customize. Every time there is a benchmark, there is the risk that you optimize an algorithm for that specific benchmark that doesn't solve the general a slightly more general problem, even the same setting, but in a different, a slightly bit more general. So it's good to have more benchmarks to understand when something has been optimized too much.
All right, that's great. Let me continue with questions for you, actually. So from Andreas, do you think that there should be a simulation-based benchmark for robot grasping that resembles your real-world benchmark?
Yeah, we actually have that. The GRASPA benchmark I was presenting is now also available in simulation, because of course it allows. It's also available in a Docker, which makes it very simple to download and run it. Now, I'm not sure how much you can learn out of transferring what you see in simulation on the real systems, but it's definitely an added value, at least to be able to just run it without any hardware, or even if you have a different robot to run it. It's implemented for a Panda arm, not for different robots, but it is available.
All right. Okay. Maybe a question that maybe it is for the round table later, but I mean, I just put it here for you while I was listening your talk. Do you believe that what we aim for in grasping is to succeed like 100% of the time in terms of success rate, or failures are something that they exist? We should accept that they will exist at some point. So we have to really understand them and react on them for to complete the task, or to save something in the environment or on the robot.
Yeah, actually, this is a very good point, because I believe that it is correct. We should not fight to get perfect performance or at least there is another way, which is dealing with failures. So just learn strategies, recovery strategies, or implement recovery strategies that allow you to recover. Because if you look at when robots fail, sometimes you see the robot grasping, you see it's grasping in a sort of suboptimal way, and you know it's gonna fail. When you lift the object, you see, okay, maybe it's falling, and then boom, it falls. So when you watch the robot, you know when something is suboptimal and it's gonna fail, or maybe it succeed by luck. But the robot is doomed. There's no recovery, right? Usually it's like open loop. You go there and you pick it up. But having some corrective actions will improve a lot.
Right, right. Okay, cool. Joao, I don't see any other question in the chat for Lorenzo. Do you want to continue with Joao with Rob Platt? Questions for Rob? Oh, we cannot hear you, Joao.
Yeah, no, let's skip with Lorenzo. Let's do it person by person, like speaker by speaker. So Julia, I think, wrote a few questions.
Yeah, I have a question for Lorenzo. Hi, Lorenzo. So you mentioned like a lot of reasons for failure are due to the specific hardware design, for example, of the IROS, but this can happen also to other robots. Do you think that actually the methods can, let's say, at some point be good enough to deal with some possible, let's say, bad designs or let's say imprecise designs of the hardware, or do you think that actually an improvement on the hardware side is required for improving the performance on grasping or manipulation?
So I think sometimes you see robots, like there was a very nice paper by Lorenzo Iamone where he was teleoperating the iCab, showing that how much you can grasp with the teleoperation. And I think there have been also other examples. So if you have a brain, the human brain, you can do a lot, and probably you can compensate for a lot of the limitations in the hardware. So that means that if you fight enough with algorithms, you can do a lot. But then there are things that you can solve much easier with the hardware. Like for example, if you have two fingers that are difficult to align, like in the iCab, sometimes one of the failures is that the thumb doesn't go in opposition with the index, and then you generate a torque, a rotational torque, and the object flips. This type of movement, you need very precise control. But if you have like a larger pad instead of the fingers, then the grasping is automatically more stable. Or the friction, if you put rubber in the fingers, you boost a lot the performance of the grasping, even if you don't know how to recognize part of the objects that are less slippery. So yeah, hardware can do a lot. And an example is those hands that are even not that the form like bags, and then they lift it up, lift object up, things like that. So, but I think also, yeah, if you improve enough the algorithms, you can compensate for a lot of the limitation in the hardware.
Okay, thank you. I completely agree.
Okay, so we can move on to Professor Platt, but I mean, for everybody else, if they want to keep on asking questions, we can go back to the other speakers. So let's see the questions on the chat. Okay, I'll start with a question of my own, which is about this the augmented state representation, where so first you kind of you choose an X and a Y position where you want to put the gripper, and from there you choose an angle, and then from there you choose like a Z height. Well, I was looking at it and I was thinking, couldn't this, instead of just seeing 6D pose, it could also be like X and Y to choose this, and then the other levels could be something else that's unrelated with pose. Could be a different gripper would grab in a different way, or so.
It could, I guess it could be anything. Can you be more specific? What, like,
That's
what,
my
for
question. So
example,
this
what are
could
you
be
talking
anything,
about?
right? It could be anything. It does not need to be like on the same domain, right? So pose domain. It could be just
Right.
about.
Yeah. So a few years ago, there was some work where I'm kind of blanking on the authors, but some folks had used an augmented state approach to solve like some of these, like a half cheetah type domain, some of these control types domains where there'll be like 5 or 6 different action dimensions. And the approach was similar where you select one dimension at a time. Now for an approach, it wasn't exactly the same, but it's kind of similar. Now for an approach, for a problem like these control problems, they're easily solved using things like DDPG or these continuous action space reinforcement learning methods, because you don't have to get the action perfectly right in order for the cheetah to start moving in the right direction. And that's the spatial action representation. It's very tricky because it's like a small change in action has a big change in outcome, as opposed to like in many other domains where it's probably not essential to get the action selection exactly correct. So anyway, I guess that's a long way of saying yes. This kind of approach it's the augmented state idea is not super popular in the literature, but it certainly has been applied in other settings. I think this application to SE3 or spatial action spaces, that's kind of an interesting connection that hasn't been made before. Because as far as I know, without doing the spatial action space, without doing like this augmented state thing, it's infeasible to do high dimensional spatial action spaces. So sorry to talk so long.
I was thinking about it because then this could be reused for other. Let's say you change hands, then you could still keep this first level of just choosing an X and Y, right?
Yeah.
Let's say you change gripper and you have to approach it in some other way, then you could still keep that what you learned for those 2 levels.
Yeah. So you could have something where so in our work, we in the latest version of our work, we have like a 5-level hierarchy where the first level chooses X, Y, second layer chooses like theta, third is Z, fourth and fifth are a couple more dimensions of orientation. But you could have like an initial layer that chooses what hand to use. Another thing the initial layer could do that we're looking at now is to decide like what general perspective to view the scene from. So in the work that we had shown with this block stacking stuff, all you need is like this top-down view. But for many kind of more real-world domains, like we look at household tasks a lot. You need to select what view you're going to see. So if you want to like do the dishes or something, you need to decide, do I want to see the dishwasher from the top or the side or whatever? So you can make those kind of decisions as well. So I think that's right. You could choose hands, or you could choose other things like just generally, how do I want to be doing this task?
So a question from Dimitri is, do you
can,
believe?
Can I jump here and combine my questions to one?
All right.
All right. First of all, good to see you, Rob.
Yeah, good to see you.
Mainly my main question is the following. So I've seen a lot of your work and I'm following it, the work you do with Andreas and Marcus. And it seems that the tasks of, picking objects in clutter and putting them in a box, it has high success rate these days. But you know, like we can reach 98%, you know, it's really close to optimal, let's say. But these are mainly on toy objects. Do you think that if we try to move to something, you know, to tools or something a little bit more challenging, so deformable objects or uh, anything that you can imagine, all these methods may start failing in one way or another?
Yeah, I agree. So, you know, that statistic you cited about 98% success. If you have a very limited, a very circumscribed grasp problem, you could potentially get there. So, for example, we had done some work with a company at one point where we had focused only on grasping these these electrical plug things. And, you know, and if we train for plugs, you know, by God, we can do 100% success, you know, even in clutter. It's like, it's great, you know, and that's, you know, and we did it hundreds of times and it like never failed. As you, you know, as you get to, you know, the so-called more adversarial objects and more challenging objects, like obviously that drops off. And like Lorenzo was saying, and others, what you really want is some ability to recover, you know, grasp success doesn't necessarily mean that you do it the first time. I guess that your grasp succeeds like on the very first attempt. You know, obviously, as long as you're, you know, human grasps aren't always perfectly successful. I guess my impression has been that what you want to focus on is doing a better job at kind of bigger tasks, because it's never the case that we're grasping in isolation. You know, we're always, if someone wants to grasp, they want to do something with the objects. So really, we should be thinking about grasps in the context of tasks, or maybe we should just be thinking about tasks. And that's certainly the direction that that we've been going. So the blocks worlds that I showed, they're pretty simple from a grasping perspective. They're more challenging from a task perspective, because it turns out it's pretty easy to knock down a teetering pile of blocks. But I think that you know, I guess what you want is to combine that. You want like challenging grasps in the context of challenging tasks. But you know, task ability to solve tasks implies that you're going to be able to like kind of iteratively re-grasp as appropriate in order to solve the task.
All right, thank you.
Yeah, sorry, I'm just given to rambling responses.
No. I'm trying to find. There was another question in the chat about for you. I think it's from Andreas.
It was from Andreas, yes.
Can you Julia? Can you find it? I mean, I'm not sure. And ask Rob.
Yes, sure. So hi, Robert. Actually, it's both for Robert and for Andrew. But Andreas says, so it seems there is a significant gap between what grasping manipulation methods can achieve in idealized lab settings and real application cases with challenging conditions. How do you think this gap could be reduced?
Yeah, I can talk about that first. Yeah, I guess I actually don't think there is a huge gap between our blocks. I hope that there's not a huge gap. Okay, I hope that there's not a huge gap between our ability to solve blocks tasks and our ability to solve household tasks, which we're trying to extend to now. The reason for my hope is that in contrast to think, plan, act, you know, kind of perceive, act style approaches, end-to-end approaches do a much better job like adapting to kind of unstructured worlds. We've already demonstrated that our method can handle novel objects, and we're extending right now to real world objects in simulation. But I think the approach that I described should be extensible at the very least to circumscribed domestic assistance tasks, such as like operating kitchen machinery or like coffee machine or whatever.
Maybe we can hear what Andrew thinks instead, so we can start having some kind of debate or just discussion.
I'm actually having a little bit of trouble with your audio. Can you repeat that question for me?
Yes, sure. You can also maybe read it in the chat. It depends when you joined, but I can read it for sure. So Andreas is asking, it seems there is a significant gap between grasping manipulation methods, between what grasping manipulation methods can achieve in idealized lab settings and in real application cases with challenging conditions. How do you think this gap could be reduced? Was it better?
So I think I would actually agree with Andrea. As you could see in the videos during my presentation, there were some environmental factors that would always mess up a grasp, lighting, things like that. Even with something simple like grabbing a handrail, which is the blue rails in the video. Actually, why don't I just screen share? Give me just a second. Sorry guys, give me just one more second. All right, so grabbing these blue handrails in order for the robot to move around the station, even going from the lab environment across the hall over to Argos changed the situation quite a bit. And they were much more difficult to grab. We had to fine tune everything. And then we just knew that as soon as we were up on station, conditions would be very, very different, and we would have to tune those again. So I think there still is a significant gap between doing something in the lab and doing something in the real world. How we go about fixing that is, in our case, we're upgrading affordance templates, which is what we use to grab the bag. And to some extent handrails, although they're simple enough. The affordance template is really just 3 positions to move to one above where we expect it, move down, and then, of course, go ahead and grab it. We here once again, we can recognize the drawer, but it's much easier to recognize with fiducials on it. So we still go ahead and put fiducials on stuff, but you can't have fiducials on everything. So there are things like that. More robust object localization, I think, will help. Give you less of a required tolerance in grabbing things, stuff like that. Oh yeah, that's kind of the short version. But I think it is something that we are improving, each year.
All right.
Thank you. I will just rejoin the meeting for fixing my audio, hopefully. See you in a few minutes.
All right. Let me continue with some questions for Andrew from my side. So I guess when you have to deal with this kind of environments in I don't know, in international space stations or other planets, etc. So all the physics they may change, right? Let's say it's just gravity. Is this more challenging to solve somehow in the current way that we try to solve grasping?
So it is to some extent. One of the major obstacles is actually having to use the system IROS, which is a gravity offset system. The actuators in Robonaut's legs are not strong enough for it to walk in gravity. It's like any time we want to test walking, we have to go get into this very large system with this large C brace here, and then there's a cable running up to the top, and it's almost like a giant 3D printer.
Right.
That'll kind of carry you around. So there are major changes like that. One of our other concerns that is much more significant with a lack of gravity is, what if we miss grasp and either the robot goes floating through the station, or the object we're trying to capture goes floating through the station, things like that that you wouldn't have to worry about as much in a gravity environment. Like maybe you knock over the cup, or maybe you just scoot the cup across the table.
Yeah, I didn't think of that.
Does that kind
So
of answer your question?
if you fail a grasp, then the object might just keep on floating forever, bouncing around the station.
Yep.
There's a few more questions on the chat for you. So Guillaume is asking, the obstacles in the path to clutter the environment are static, apparently. Planning could avoid them even between motion steps. Was there some online collision detection? When I assessed lots of obstacles could float around all. So was there?
Yeah, so this goes back to the same thing. Objects can be floating around, which is one of the reasons we do a scan, in this case, before each step. Having more active scanning is something we're looking at as we're trying to kind of plan out the next robot we're going to build, putting more sensors on it, a lot of point cloud-based sensors to detect basically what space is filled. In this case, we're using an Octomap, which worked pretty well for us. But yeah, things are going to be pretty dynamic when everything can float around. If you ever see pictures of the actual space station, almost everything is strapped down. Like think of kind of like luggage. I'm drawing a blank on the name, like bungee cord kind of luggage straps.
Which brings me to a question that this is a general question. Maybe we can also talk about it on the later on when we're having the round table. But when you're grabbing the surgical tools, it seems like you put a white backdrop to segment it better, right? To be easier to segment. Like in general, how much are we willing to go in terms of like engineering the environment to make it easy for the robot to do stuff, to fail less? In a for example, in a factory, we're willing to go a long way, right? How much are we willing to go in our houses or in a space mission to engineer the space around so that you fail less, that things work better?
So that is actually something we have been in negotiations with the designers for the new station modules for Gateway, having them look at an interface that's just a little different for a human versus much easier for a robot. There are some interfaces where you have to kind of pinch your fingers together and then like pull out a connector, which is pretty easy for us. For a robot, that's really difficult. So in our case, since we're literally engineering the entire environment, similar to a factory, but I think it's safe to say even more so, we have some options of give and take with the designers. But back to you can't put a fiducial in everything. So when you get out into the real world, you can only go so far.
Okay. What about regarding hardware failures? How about modular devices? For example, switching from an end effective to another.
So that is actually, taking a step back before getting into that, the next generation of robot we're looking at will be more modular. It won't be humanoid, all the 4 legs will be the same, things like that. And that should help us a lot with that kind of problem. just having different capabilities. Looking at changing the tool for different tasks, I was actually in a meeting about that about an hour and a half ago. We're trying to develop a tool changer, which is also doubles as a mobility interface. So it would be kind of like the feet, grabbing the blue handrails that you saw just a few minutes ago. It would fulfill that function as well as be an interface for tools to be connected, be those a gripper or something more specialized for a specific science or research task. But yeah, that's a major question. You can't do everything with the same gripper. In the case of Robonaut, the hands were actually designed first and were designed to function like a human hand so that Robonaut could use all of the tools already on station.
So the last question for you seems to be, which types of robot manipulation framework did you use for faster grasping on folding objects in space like bags? So do you grab these folding objects, these like more flexible things like bags?
Yeah, so I've actually stuck it up. Let me just reshare my screen. That should be the right spot. Yeah, so the bag here is actually deformable. And that is one of our failure cases, although with the fiducials, one we don't see as often, is basically you squish the bag too much and then miss the handle, which it's grabbing right here. But yeah, even things like moving around the station with one of these bags that is deformable, you don't have a rigid grasp on the handle, is a concern. Catching it on something as we move through the station, banging it into another piece of equipment, things like that.
And you're just assuming it's rigid. Let's say you're planning as if it were rigid.
That's actually something we're still looking into, because yeah, we have to know where the bag is to make sure we don't hit anything. So what that interface looks like is still kind of in question. There is also another robot on the station called Astrobee, which may provide like a third-person view of the robot moving and help us to localize the bag effectively, even when it's in a grasp. But yeah, deformable objects always come with their own fun problems.
Yeah. That's something we should definitely talk about in the later today. Deformable objects. So I think we're done with questions for you. Tony.
Sounds good.
Tony,
I am going to step away for a minute, but I will be back shortly.
All right. Okay.
Oh.
What's up, Tony? So Dimitris asks, you focused a lot on the definition of a failure. I think this is important. So do you believe that grasp failure should be defined with goal set of tasks or with the stability of the grasp itself?
And can I clarify what I mean here? So let's say that your goal is to take an object from somewhere and put it in a box, but it's like 100% that whenever you are above the box, this slips and falls in the box. So you complete the task, but this is a really bad grasping failure. So is this a failure, or this should not be considered a failure? So it is a task based thing that we should define, or really, as the definition of a grasp defines a failure?
I think it depends a lot on the task, really, but yeah, it basically, if it succeeds by chance, basically, and with the same behavior from the system, it could have failed, then I guess it should count as a failure. But if the whole sequence should succeed, although it's true that in some cases you might have some failures that you can correct. In that case, if it succeeds because you corrected the failure, maybe it could be counted as a success.
All right.
Can I jump here and say something? Because I was thinking that maybe you can also considered, so basically we consider some kind of grasps like successful because they're really repeatable. So let's say the variance on the success is really small. So it's really stable, robust, whatever word we want to use. So actually, if we have like that, our robot can solve the grasping or do some kind of tasks in a very original way that looks maybe like it's not doing the grasping task exactly, but if they are able to do the same, I mean, if you're able to reproduce the same behavior like every time, I think at that point you can consider that a success. So it can also be like on the reproducibility of the behavior.
Yes, yes, I agree. If you remove that element of chance, if it's consistently succeeding, then yeah, you could consider it another way of performing the task.
So should I keep going with your questions, Amit? It seems that some objects just cannot be grasped due to friction. Do you believe that there should be hardware solutions or software solutions for when it's just sort of like impossible almost to grab something?
Well, I guess in some cases you would require hardware solution. Like if I don't know, if the payload is not enough, you might have to change the arm. If the object is too big, you might want to have like 2 hands or a bigger gripper or something like that. Or being able to use a caging grasp if you have a big slippery object, you might need a big gripper to cage it or something. In other cases, maybe the software solution is enough. Like you could control better the position or the force. You could use caging. There would be ways to see if you can generate that friction or to sort it out. But I mean, in any case, it's true that hardware improvements will make it easier. So you might not have to work so hard on the software side if your hardware is a bit more forgiving in that respect. Like for example, having higher friction surfaces or yeah, flash that is adaptable to the object geometry.
Okay, and when you're it's been discussed a couple of times already today about having reliable simulators in the sense that if something fails on the simulator, is likely to fail also in reality. What do you think it's missing from this correspondence between simulation and reality? Is it on the level of the contacts? Is it on the
From our experience, the contacts are not very well simulated in general. It's kind of difficult to have the same behavior that you would get with real materials. And also the fact that you would want to characterize different types of materials in terms of friction or in terms of deformability or compliance, that we haven't found any simulator that does that. Allows you to determine the materials of the surface of the two surfaces and then simulates realistically what happens when they are in contact. So that's one thing, and also that is related to tactile sensors. So you want to have tactile sensors. Then if you're unable to simulate contacts reliably, then the data that you get from those simulated sensors will not be very
the
good.
signal will be something totally different as if of what it would be on a real contact.
And I have just a question. Can I ask a question? Okay. And I think that the friction is a very critical point for the grasping manipulation system. And for example, human hand, the friction coefficient may change if you put the brace on the hand. So I think this is a very critical point. Do you have any idea on how to solve, how to overcome this problem?
Apart from using better materials, no, like using probably some materials that are a bit similar to the human hand. But yeah, I'm not sure if we don't have to go so as far as changing the friction as you change pressure, but at least some surface that deforms a bit around objects that are small, for example, can be very useful when you try to grab small objects. Having something that deforms around the object, that's certainly going to help a lot. And in our case, also having good tactile sensing in the fingertips can help as well. And sometimes you can detect slippage by the vibration, and that will allow you to correct by either, I don't know, pressing harder or pressing less, if that is what's going to help, because sometimes pressing harder makes the object actually slip away from the fingers, depending on the geometry.
Yeah, thank you.
I wanted to ask just a brief question, maybe to Tony, maybe to others. So, yeah, we've had real we use PyBullet lately, and one of the things we tried recently to do was generate grasp labels by measuring whether PyBullet succeeded in picking up the object. And this turns out to be a very noisy measure of a very noisy way to get your ground truth labels. So yeah, does anyone know about like grasp quality metrics for PyBullet that exist in PyBullet? Like grasp quality metrics, I would say is, you know, probably a more reliable source of ground truth grasp data. And we had been using, in the past, we've been using antipodal measurements, but in our own kind of thing. And now we're using PyBullet. Now I know that the Columbia GraspIt simulator, whatever that was, they had these grasp quality metrics built in. Does anyone know if something like that exists for PyBullet? Yeah.
No, I don't.
No, this seems to be a very good idea. So rather than letting the physics engine decide whether it's going to be a success or failure, you'd have say an analytical model like a wrench space or something that kind of bypasses the limitations of the physics simulator.
Yeah, I would say that you know, there's probably I think there's recently been a fair amount of discussion about which quality metric to use, but just using like basic like Ferrari canny wrench space type metric.
Just something like that.
I guess they don't have it for PyBullet though. Oh well.
Yeah.
I mean, one thing you can get out of PyBullet that we were probably going to use was just to like measure contact positions and contact normals. And since we mostly use 2-finger grippers, I think we can just reconstruct it from that.
It's easy to construct that. But I was thinking, like, when everybody thought that these metrics were gonna die, maybe they'll have a comeback now.
Yeah.
And,
Well, I mean, there was
okay.
like a couple of years ago, there was like major discussion about this business about the metrics. I don't know. Maybe that was just maybe it just seemed that way to me, but it wasn't actually happening.
There have been a lot of discussion on the grasp quality metrics, and I think that most of the researchers use the metrics proposed by Ferrari and Canny. But I think that this is very critical. And first of all, as I told you in the previous discussion, that the friction is not correctly identified. This is one of the big problems. And also, if we compare the grasp quality metrics with real case, sometimes we often encounter difficult situation where the grasp quality metrics doesn't match with the real situation. So I think that this is this is not major. No, this is not a well-known point, but I think that this is a very important point which has to be solved.
Absolutely. So both the friction and the fact that when in a real situation, when we close, we might displace the object a little bit, right? So what do you think? Where do you think your contacts will be? Might not be where they end up being after you kind of after you contact, because one finger is going to contact before the other one. So you might get a wrong assumption on the
yes, and also grasp quality metric cannot deal with such a intermediate situation.
Yeah.
So that is also another problem. Yeah, I agree with you. Yeah.
Yeah, I will say, so about this business about the object shifting in the grasp, so it's true that this is something that a simulation could capture that a metric would not capture. But one of the things that we are usually, when we're doing simulations, what we usually are trying to measure is some kind of ground truth to use to train some machine learning algorithm. And like if you're training like the grasp detector, then it's sometimes desirable to have like a really conservative notion of grasping rather than teaching your grasp detection system to rely on a particular shift of the object. Maybe you want to train your grasp detector to generate grasps that are successful without shifting the object. Yeah, so actually that's one of the things we were thinking, you know, because with the pi bullet sim, you know, the contact dynamics were wrong, but we were often like, one of the reasons I thought that we were getting noisy predictions about grasp success or not is because a lot of crazy grasps can be successful because they, like, you know, pi bullet will just rotate them and, you know, and it just falls into the grasp. And those are things that you don't necessarily want to rely on happening on the real robot.
Okay, let me just now go back a bit to this question of the metrics. I'm going to unmute Cindy Grimm, who is now working on porting a metric, a grasp quality metric to Mujoko. So did that work? Unmute.
Okay, sorry. I'm on my phone while trying to hold office hours, so this is a bit tricky. Yeah, we just have finished, we're wrapping up a paper for ICRA where we've basically done a whole bunch of metrics that are based a little bit more on measuring the space between the hand and the object. We've done them in Mujoko, and we're looking at shifting to pi bullet. So, I mean, basically what it comes down to is not relying on contacts to do the calculations per se, which makes them a little bit more robust. It's more about the distance between the hand and or how the hand is oriented, the fingers are oriented with respect to the object. But yeah, if anybody's interested, we will be porting those to pi bullet very shortly since we're shifting to pi bullet. So yeah, if anybody's interested, let me know. Yeah.
It seems like a lot of people would be interested in that. Yes.
Yeah.
Okay, so let's go back to the chat and see for Professor Arada what questions we have.
I just asked questions to Guilhem work. So this is just the answer to the question. So
but okay. So you want to
entanglement, prevent entanglement.
So yeah. you wrote the replies. Okay, well,
yeah,
maybe
right.
you can just talk about.
He asked question about the flexible and deformable object may often cause entanglement. So I answered that this is definitely the research topic.
Yeah. And what about? There's also a question about collisions. So neighboring object collision. You predict collisions that may bring failures and avoid the corresponding grasping. What if you need to grasp a particular object for a particular task? Is this method failing in this task?
Yes, and I propose the method to predict the contact between the neighboring object. But it depends on the shape of the object. And what I proposed about 4 years ago is a very simple method, and depending on the shape of the object, the physical phenomena will be more complex. So at least my method can work for simple shaped object.
Okay, and for another question for the entanglement where you try to remove these pieces. Did you consider like doing what people do, which is sort of?
Yes. This is what I haven't published a paper yet, but this is what I've been researching, and there are many different motions of the manipulator to resolve the entanglement. So definitely there are a lot of room for research.
Mm.
Yeah.
And this also comes to another question that I would like to bring later, which is about dynamics, which is about
Yes,
accelerations on the.
Yeah, it also depends on the dynamics, and we can use dynamics to resolve the entanglement.
Yeah.
Yeah.
So recovering from an error state is very interesting. Do you think that instead of planning the perfect grasp, online adjustment might be a solution to several grasp failures?
Yeah, of course, yeah, definitely, yeah.
Okay.
Yeah.
So so it's 2 o'clock here, whatever time it is where you are. So maybe we could go on to the next bit. So the next bit is I'm gonna share my screen. And I'm gonna be presenting slides that people contributed to, and then maybe for each slide we could have 5 minutes between the person. So I'm gonna unmute the author if I can find if they're here and care to put like first name, second name. I'm gonna unmute them and then maybe we can talk for a minute or two about each contribution. So let's start with.
João, before you do that, let's ask also the invited speakers to stay there, because we will have a small round table after the posters.
Oh, yes,
right?
yes.
Okay.
So let's start with Alberto Camacho, and Alberto is from Google, and his contribution is called Disentangling Planning and Control in Vision Based Robotics by Reward Machines. So if I can share my screen now. This. And I'm gonna try to unmute you. Okay.
Okay.
Okay. How does it look? Can you read can people read what's on the slide?
Yes.
Okay. Yeah, so thanks for the introduction. My name is Alberto Camacho, and this is joint work with Jake, Andy, Dipali, Atil, and Dimitri from Robotics at Google, New York, on disentangled planning and control in vision-based robotics via reward machines. And so I want to start this presentation with a phenomenon that we found in DQN when we wanted to train it in a very, very simple block stacking task. So this task only has 2 blocks, and the goal is to stack one block on top of another. So in abstract, we have only 3 stages. In the first stage, the initial state, the 2 blocks are on the table. Then what we have to do is to simply grasp or pick one of the 2 blocks and then place it on top of the other one. So DQN fails. Why does it fail? Well, we looked at the Q value heat maps that are in the image that you see in the top left corner. So these Q value heat maps show the Q value for each of the XY coordinates of the target location of the gripper for the action place and the action pick. And the first thing to observe is that these Q value heat maps look very similar to each other, even though the optimal action is clearly pick and not place. So because they look very similar to each other, when we execute the policy, DQN has a high chance or high probability of choosing the wrong action, which is place, and fail to grasp. Okay, so we understand the problem. How do we solve it? We built on top of an existing framework for RL that is called reward machines. So what is a reward machine? A reward machine is just a graph provided with structure and rewards. And this graph has nodes, right? What are the nodes? The nodes are abstract states that tell which point along task completion the agent is currently at. And how does it work? How can we use reward machines to train RL agents? Very simple. Reward machines extend the typical or standard RL loop. So now reward machines observe the observation from the environment as usual and update their current state, the node, according to the observation. And now we also extend the RL loop with two pieces of extra information. One is abstract states that tell where the reward machine is currently situated at. And the other piece of information is rewards, denser rewards that tell whether the agent is doing well or not. So intuitively, these rewards will be positive if the agent is making progress along task completion in the reward machine graph, and negative if the agent is moving backwards along task completion. Okay, so now we trained DQN with reward machines, and we look at the Q value heat maps. So the first thing to observe is that the Q value heat maps for the action place and the action peak, now they look different to each other. That's good news. And the second thing is that the Q values for the action peak are higher than for the action place. And this is also good news because the optimal action when there are two blocks on the table is peak. Okay, so we continued with our experiments and we tested DQN with reward machines compared to different ablations of DQN, where we used DQN extended with reward shaping, but without abstract states. Now the opposite, DQN augmented with abstract states, but not with denser rewards. And finally, standard DQN with sparse rewards. And there are also two things to observe. The first thing is that DQN with reward machines learns better quality policies and also learns it with fewer training steps. So in summary, reward machines can be useful to train RL agents in vision-based robotics. Reward machines can guide the agent via denser rewards, inform the agent about task progression via abstract states, disentangle planning and control, and we have seen it because the Q-value heat maps look very different to each other, and finally, improve sample efficiency compared to vanilla DQN. So with this, I conclude my presentation. Thank you very much for listening. And if you have any question, I'm happy to answer them, or please feel free to contact us offline. Thank you very much.
Yeah, thank you. Thank you very much, Alberto. Maybe you can ask a question or two. Maybe Dimitris wrote here, and maybe you could also extend this question to Professor Rob Platt. And this is about the action state representation. So Dimitri is saying the main problem in reinforcement learning might be the action space. So here you focus on task space and continuous versus discrete states. Do you believe that a cause of failures in grasping and manipulation is due to the action state space representation?
Yes, that's a good question. Good question, yeah. So what we observed is that the action space is quite large because we are in a pixel space. And in this pixel space, only a very, very small number of actions that are the coordinates of the block are the good actions. All the other actions, and there's a huge number of other actions that are bad. So the state representation does matter. If we were able to kind of abstract the state space via some post-processing that we have not done and simplify all the bad XY coordinates versus the good XY coordinates, that would kind of, I think, help. And in some sense, that's what reward machines are kind of doing, kind of maybe orthogonally, but in the same spirit. Reward machines give an extra input signal to the agent that say, hey, you are in a state in which you should be picking versus you should be in a state in which you should be placing. Now, reward machines don't tell you what you have to do, but it tells you that you are in a special state in which you have to do something that is different than what you have to do in another state. And the RL agent has to figure out which actions have to be done in each abstract state. So definitely state representations do matter to RL. And the more you can simplify or abstract the state representations, the better. The more hints you can give to the RL agents, the better as well. I hope that kind of answers some of your questions.
Yeah, Professor Pat, do you want to unmute and maybe ask what you wrote here? How do you define the abstract
Yeah,
states?
sorry if that's confusing. So the reward machine, essentially, from what I understand, it seems to be encoding some expert. Basically, you're providing some additional expert supervision. The humans providing that, or where's that coming from?
So currently, we presume that the human, the designer of the task, is providing this description of the task in the form of a reward machine.
Okay, and then my understanding is that the Q function is being learned via a bandit, like the Q learning is now like a bandit problem. Maybe not. Okay.
Not yet. Not in general. No, there's now it's one way to think about it is that it's a standard RL in an augmented state in which now states are, as usual, observations plus extra signals coming from the reward machine. So it's the cross product. If you want to think about it, now states are the cross product of observations and reward machine states. So it's just a standard RL problem.
Yeah. Okay. Yeah. So sometimes please cut me off if we need to move on. But I guess sometimes I think about expert supervision by thinking about the expert might provide one-step rewards to a bandit, which is learning a Q function, which sounds similar, but I guess you still have a TD error in there.
Yes. Well, one thing that we are kind of found is that depending on how do you distribute the rewards, you can transform it into a kind of a supervised learning problem, which maybe aligns more to what you were suggesting. Like maybe in the limit, the more information you give to the.
Yes, in the limit, maybe it would become like I was saying.
Yeah.
Yeah. Okay. Let's just can I interrupt and just move on to the next one, because we have to go through 5 of these. So the next is Roberto Miatini. Let me unmute you if I can find you. Oh, I found you. Okay. Roberto, so this is Roberto Miatini from Bologna, collaboration with the DLR in Germany. And the title is Remarkable Failure Story in Close Human-Robot Interaction, Advanced Biocontrol of Prosthetic Hands.
Okay, thank you. Hello to everyone. Yes, this contribution is a collaboration between the University of Bologna in Italy and the German Aerospace Center. Yes, and my name is Roberto Martini. So in this contribution, we are considering the control of robotic prosthetic hands by means of myocontrol, which means using electromyographic signals or EMG along with machine learning techniques to decode human grasping intentions and command the robotic prosthetic hand. This kind of control interface is already implemented, I have to say, in several commercial systems, but at a very basic stage of development. And this happens because academic advanced myocontrol techniques, which aims at controlling continuously and simultaneously multiple degrees of freedoms, are evaluated as unreliable by the users. That is, this algorithm fails in repeatedly understanding the correct human intention. And among a number of reasons, one of the most important regards the problem of inconstancy of the EMG signals gathered from the muscles of the users. So in order to face this interoperation problem, we therefore formalize this unreliability of myocontrol in the form of myocontrol grasping failures. That is, we consider that sometimes the myocontrol correctly detect the user intent and execute the desired behavior of the robotic hand. Differently, other times for some reasons related to the deterioration of the EMG signals, the microcontroller fails in the detection of the grasping intention of the user. And we therefore proposed a framework to deal with this problem based on the approach of incremental learning. And specifically, we use an incremental variant of the ridge regression algorithm to allow occasional updates with a modest amount of novel training data to enable the possibility of a continual adaptation to the changes over time of the EMG signals. So we name this paradigm interactive learning microcontrol, in which a microcontrol scheme should be updated preferably in an autonomous fashion also. Therefore, an important aspect also we have started to investigate is related to the automated detection of grasping failures in this context of microcontrol. And we obtained preliminary promising results trying to detect failures using a minimal kinematic based measurements from the robotic end, but we are still studying several aspects. And we have some research questions we are currently dealing with. And some of the most important are related to what are the best signals in order to extract the information of the occurrence of a grasping failures of the prosthetic robotic hand, how to effectively window in the data for the updates of the machine learning algorithm, and how to correctly then label this data online in order to enforce a consistent update. So that's all, and thank you for your attention.
Okay, thank you, Roberto. I do have a question. So I like that idea. This approach seems really interesting, but what you're assuming here is that, if I understand this correctly, is that these errors, these failures, will never be due to the human doing something wrong, right? It's always the system that misunderstood what the person wanted to do. Is that correct?
This is a very central point, I think. You just mentioned a very central point, because one of the problems we have encountered when we started to formalize and systematically deal with this approach is that, for example, when you do autonomous grasping, okay, if the object, for example, fails from the hand, it is a grasping failure. According to what you are evaluating, okay, but it's a grasping failure. Instead, if it happens during the operation of a prosthetic hand, you have the doubt that maybe the user opened the hand simply. So indeed, one of our questions is what signal to use to detect these grasping failures, because we think we should also use measurements, in our case, biological measurements, but in general, measurement to understand the human intentions, in order to also understand if what the grasping that is executed by the hand match with the user intent. There is always this second condition. You have to verify if it's matching the user intent or not.
Hmm.
I don't know if I answered.
Yeah, and that's a big, huge problem on its own. I'm just gonna, I'm just gonna have to move a bit forward, because in the interest of time, we need to go on to the next.
Thank you.
Thank you very much, Roberto. So next is Benjamin Panrek from Buurthogeschool, and he's presenting model-free monocular visual servoing. Let me check if I can find you. There you go.
Okay, perfect. Thank you very much for introducing me. In this work, we used the case that failures, inaccuracies, and lower speeds for grasping objects are explicitly allowed for humanoid robots in most human-machine interactions. And the important constraints of our hardware that we used here is that we only have 4 degrees of freedom for each arm. So you can see on the left of the side, 1 in the shoulder, 1 in the elbow, and 1 for the wrist rotation. And we also have only a monocular camera system without distance measurement. Our approach uses sensor motor loops for the head, for the arm, and also for the wrist movement, and creates an emergent behavior, which is called gaze heuristic. And this is the well-known strategy in behavioral psychology. A huge advantage of these sensor motor loops is that they are independent of calibrated proprioceptive sensors. So they require no calibration, be it the joint angles or the camera position or the optical distortion of the camera. When we move the arm or the hand closer to the object we want to grasp, and we have to avoid the final collision of hand and object or hand of table, we currently use quadrics, which are learned by recursive least squares method. And for this method, we move the arm of the robot or the hand of the robot on the table surface with a relaxed elbow joint to learn the implicit model of this table surface in the joint space. And our experiments have shown that 3 kinds of quadric surfaces are dominant. First, it's the ellipsoid, which is the mathematical optimal solution for this. The elliptic hyperboloid of 1 and 2 shells are the second and third one. And on the bottom right, you can see this quadratic surfaces. Shown here is the hyperboloid of 2 shells, which is the optimal solution for us, not the mathematical one, because this gives good estimates of the table surface outside the explored points. That could happen when we cover just a part of the table by the learning phase. Maybe the rest is covered by an object or so. Yeah, in the end, this method works very well for this autonomous embedded system we have here, and especially works with low calculation costs. But because of the fixed position of the head, the parallax error between hand and object depends on the position of the object, and it works better as closer the object is placed to the body. Yeah, currently we are looking for easy heuristics from the trial and error type to build an empirical knowledge, like an offset map or so, of the hand to the object in the visual image to tackle this parallax error. Yeah, thank you very much.
Yeah, thank you, Benjamin. Let's see. So this is a problem. I think some of the things that you've spoken today also match with some of the issues that Lorenzo was talking about earlier on of having a human eye, right? And also the ICAB, as far as I remember, also doesn't have 3D vision on its own. So that's another issue. So what Dimitri made the question here on the chat. One of the outcomes from today's invited talks were that some failures may be resolved with a different hardware configuration. Why did you select to use a monocular camera?
I haven't. Could you please read it again?
Just the question is just why use a monocular camera that doesn't give you that perception of depth?
Yeah, okay. It's one of our research. Yeah, it's our research topic to find solutions with less calculation. And Initially, this robot was developed for an speech interaction project, and now we reuses this hardware for this grasping task. And I think it should be possible to find solutions to work with this low power hardware as well. And yeah, that's a challenge in this case.
I see. All right. Thank you very much. I'm gonna have to move on to PowerPoint. And the next person to present will be Alex Nitrevsky from Hochschule Bonn-Rhein-Sieg. So if I remember correctly, let me unmute you.
Hi.
Hi, Alex. If I remember correctly, you're doing you're studying this thing of failures in grasping in depth, right?
Failures in general, actually.
Failures in general. Okay.
Yeah.
So I'm gonna have to switch the share screen to another app. So is it okay if I just do this like this? I just share like this.
Yeah. Thanks a lot. So yeah, hi everyone. I'm Alex from Bonn-Rhein-Sieg University in Germany. Thanks a lot for having me today. Yeah, so my primary domain is actually domestic robotics, and in my PhD project, as Joao just pointed out, I am looking into failures, namely strategies for analyzing and avoiding failures. So over the years, I've had an opportunity to look into different types of these. But today I would very briefly like to discuss one particular category of failures, namely ones that are caused by the fact that a robot may not actually understand what it's manipulating, particularly when it comes to the physical properties of objects. So on the slide and in the video that I used for accompanying our submission, I showed two illustrative examples, illustrative failures that our robot has experienced. We have a Toyota HSR robot here. Yeah, so I should mention that in both cases we were grasping an object, and we use a very simple grasping strategy which grasps from the side. So we detect the pose of the object and then we go from the side. So these are particularly interesting because, so in the first case, it's a ball, it's a very soft ball, and the robot pushes the ball while it tries to reach it. And then, of course, because the ball is pushed away, the robot cannot grasp it. In the second case, we have a toy, which is soft and deformable. So then the robot initially grasps it correctly, but then while moving the hand back, the toy slips out of it, out of the gripper. So I think this is actually quite a general category of failures which occur in robotics, particularly in domestic robotics, because we have to deal with a lot of objects. So I think there are at least three things we can do to avoid such failures. So first of all, I think we need to use multimodal information as much as possible, particularly in order to recover from state estimation problems, because state estimation is quite challenging, as was pointed out in some of the talks today already. A lot of failures are caused by it. So also in recent work, it has been shown that contact can be very beneficial. So combining contact plus visual information can be very beneficial and can improve reliability. And this is also something that is discussed, I know, in tomorrow's talk by Dr. Bog. She's discussing this very nicely and in more detail. Also, when it comes to domestic robotics and the fact that we may actually encounter unknown objects, I think it's actually very important that we have our robots be able to actually experiment themselves with the objects in a directed way. So there is some already work on active learning for object properties. And actually in my work, I'm also looking a little bit into this direction. But in any case, I think this is something we want our robots to be able to do. Finally, I think, or I have the feeling that maybe with the rise of end-to-end learning and the great successes that we've had there, we may have discarded some structured information, for example, in terms of object ontologies, a little prematurely. Although I know there is some recent work that is sort of trying to bring some of this information back through the architectures which we use. But in any case, I think we should ideally kind of work towards finding a way to use structured information plus learned models sort of together, as they can in fact reinforce each other, and particularly when it comes to this learning by experimentation. We could have structured information guiding the learning process, while on the other hand, the learning process could be used to improve the structured model over time. So yeah, that's my short description of our work. Thanks a lot for the attention. And if there are any questions, I'd be happy to answer.
Thank you very much, Alex. So you'd say one of the key things there is multimodal sensing, right? Well, does that mean vision and tactile, or does it mean something else?
Yeah, it could be visual information plus contact information. It could, I mean, I know that sound is not used that often, but of course sound could also be useful. For example, we could hear some hit when we touch an object. Even if we don't have some tactile information, we could use other types of information. But in any case, I think just relying on one source of information, for example, visual information, is usually not optimal, because then we are prone to the errors that we have due to one.
You lose that redundancy, right?
Exactly.
And then let's move on to the last one, because we want to be finished. We want to be finished before, like, in half an hour. So, schedule. So the last contribution will be Massimo Roa from DLR, with Werner Friedl and Ashok Sundaram, and they're presenting a poster called "Robustness and Performance in the Failures in the Clash Hand." So I had the pleasure of working with Massimo recently on to see this hand, which is really cool. So I will try to find him again on the list of disciplines. There he is.
Yes.
There you go. Hello, Massimo. How are you?
Hi. Very
How
good.
you doing?
Hello, everyone.
Take it away.
Thanks for having me. So basically, we compiled this set of slides to show a little bit the work that we've been doing with the Clash hand. So for those of you who have not heard of the hand, Clash stands for Compliant Low-Cost Antagonistic Servo Hand. And the main feature that we have in this hand is that we have variable stiffness actuation, such that we can change the stiffness of each finger individually. On the hand, we can also have a number of sensors, tactile sensors, proximity, force sensors, such that using all of them in combination, we can have a very robust behavior of the hand. And we've been working in this topic of robustness, failure detection, how to robustify the application from different perspectives. So I compiled just 3 short videos. Maybe you can move to the next slide, Joe. Perhaps you can put it on presentation mode such that it can.
If I do that, is it still visible?
I hope so, yes. It's working. Oh, but the video doesn't play?
Mm, okay.
Interesting.
Oh, yeah, I think I know what it is. Maybe it's this protected view.
Oh, yeah.
Okay.
Shows us an image. Okay, so I placed the web link over there. So in case you guys want to take a look, you can do it afterwards.
Yeah,
so
let's try that.
Yeah, the videos on YouTube are actually much longer. So
yeah, let's just try that.
maybe I can just tell you a little bit and then we jump to the next slide. So this hand was originally developed within the project SOMA, standing for soft manipulation. And basically what we wanted to do is have a hand that was suitable for an use case offered by Ocado, an online grocery store in the UK, where we could just retrieve vegetables and fruits online and then using this hand for distribution of fruits and vegetables without damaging the fruit. So for avoiding damage of the fruit, it was quite important to regulate the force that you apply on each individual object. So one of the nice features of this hand is that we have this agonistic antagonistic actuation, which allow us to apply, change the stiffness while keeping the same position of the fingertip, which is not common on variable stiffness hands. So if you have tendon actuation, basically, and you want to modify the stiffness, in most of the designs, rigidizing the finger, for instance, means that you move the fingertip. So then that changes the location of the grasp. Good. This was the motivation for this hand. Maybe we can go to the next slide, Joao. Sorry that this would
yeah,
be
I need to switch back.
cumbersome.
I need to switch back to the other thing, I guess.
Okay.
Sorry, there's been a lot of technical issues during this presentation.
Okay.
Does it work now?
Yes, it works. So yeah, no worry, just leave it like that. So basically, using this combination of tendon actuation, variable stiffness, and sensors embedded in the hand, we have a very compliant behavior. So on the top, there should be a video that basically shows that with just a business card, when you try to touch the
robot by
finger,
definition is a robot made of things that are not.
Sorry, when you move the finger and you touch the finger at any of the links with something as light as a business card, the finger will detect the contact and will start to wrap around the object. That's what we show the top picture, and the bottom picture basically shows that we are very interested in having a very robust mechanism. So we tried with the DLR standard test, which is having a hammer and then hitting all the fingers and see if actually they resist. And they actually do, but we wanted to have this test as a more standard way to try fingers. And we worked with IIT, with Francesca Negrello and the team at, from PISA and IIT, developing one standard benchmark to try to test resilience of the hands. So basically how much impact you can resist without damaging permanently the hand. Our idea is that even if you have unmodeled objects on the scene, you can move around, hit the hand with some unknown object, and still you will be able to keep the grasp in the hand. And then the final slide is to show, yes, maybe we can put it, at least the image will illustrate it. This is to show that we are working on this topic of error recovery. So basically here the use case was how to empty this bin full of the same object even in different layers. So combining the sensor activity of the tactile sensors and the proximity sensor, we can very quickly detect if we failed on the grasp and then go back and retrieve the action until we can actually empty the bin. Moreover, we've been doing tests on how much performance can we get from the hand, even if we have hardware failures. So what happens if one of the motor fails? Can we still achieve 100% of the performance? What if one of the sensors fails? Or what if one of the tendon breaks? And we've been doing this kind of studies. This is on one paper that we published in Frontiers earlier this year, where we proved that even with those failures, we can still adapt the grasp plan such that we can achieve performances of 70 to 80%. So still pretty good to keep the line working while there is some servicing coming to repair the hand. So this was the quick summary of the contribution that I wanted to show you today. Sorry that the videos didn't work, but I hope you can watch them on YouTube afterwards.
Yeah, all right. Thank you so much, Massimo. So there was a question for you, but you answered it already about. I mean, one thing is highlighting the importance of when we're talking about failures. This is something that we didn't think about. Like, it's important also that the hardware is robust and reliable, right? So what the fact that failures might be an outcome of a motor that breaks and a broken tendon. Is your benchmark plan to be extended to such failures that happen during a grasp?
No, actually, yes. So actually the benchmark was intended for testing just the mechanical robustness of the hand. So you have the hand, for instance, and basically we have, same as the mechanical impact test, we have a pendulum that hits the fingers in different directions at different heights. And when we verify how much energy you can absorb from the system before the breakage of the system, basically. So it was intended in a slightly different direction. The second part of that benchmark was grasping an object and then again hitting with the pendulum until we could verify the level of energy that you could apply such that you could still hold the grasp, which intended to reproduce somehow that you would grasp the object and then maybe hit something and you would like to keep the grasp very robust. So the benchmark was not intended in that direction. For these hardware failures, we did more of an initial proof of concept study where we manually introduced failures on each one of the components. And then we used a benchmark for pick and place actions where we basically have just one object on one tabletop surface. We try to grasp it from different directions. And then with this benchmark, we'll verify how much performance we would lose with which one of the hardware failures. But the nice thing is that having these online compensation strategies, we could actually recover the failure and try to keep as much performance as possible.
Okay, thank you so much, Massimo. So that leaves us 15 minutes now to have sort of wrap it up in open discussions type thing. So I'll just ask the first thing that I think came up a bunch of times this today is it has to do just with the, let's say that we can separate these failures into things that happen in hardware, things that happen in software. In hardware, we can also consider let's say the physical world, right? So there's problems that happen in the physical world, problems that happen in the digital, whatever. There's this thing that Massimo just mentioned about having reliable hardware, right? Things that don't fail, things that don't break. And then there's also these assumptions that we make, right? Friction would be the most obvious, I guess. Can we think of other things in the real world that keep on happening to us, keep on making the grasp fail. They have to do with, let's say, the physical world, not so much about drones and planning or calibration. Can we start with that? Does anybody want to say something?
Yeah, maybe, I mean, across all the talks we had that people were mentioning issues with hardware, mostly with friction or design of the hands, but this was mostly when robots have multi-finger hands. So it seems that maybe, of course, if you have a hand with multi-fingers, it's much more like flexible, but it's also harder also maybe to impose like the proper friction, while having maybe a gripper can be a bit easier. And then another issue people were mentioning is perception, of course, because perception from real world is pretty different from what you have like in perfect data set. And also, I think another good point to stress, and also like Lorenzo, Tony, Janet, so they mentioned it today and Janet will mention tomorrow, is that it's super important to have a closed loop and a continuous feedback. And as Lorenzo was saying before, maybe like what our algorithms should do is start to like deal with the failures. So try to find a way to, instead of having like the perfect algorithm, just have a way to recover from failures. So I mean, in my opinion, like hearing all of these discussions, these were the measure points. And I'm actually maybe curious if like, maybe this is like a never ending discussion, but people that let's say, believe or embrace end-to-end approaches think that actually we like doing everything end-to-end, you can cope with all these problems, or if instead it's better to solve like individually all the issues, all the problems, and then put everything together. Yeah, this is not really a question, it's just like random thoughts that I have.
Yeah, I guess this is Rob Platt. I guess I think that end-to-end approaches can help with that if they're trained at the level of the task that you're trying to accomplish. So if it's just grasp, then that's not. So the end-to-end method has to have in view what's ultimately you're trying to achieve.
So I have a comment maybe here. So I see your point, but it seems that like now in the last years, we are kind of getting back in putting information or structure inside the end-to-end approaches. So, and you were doing also the same, Robert. So it seems that maybe like the huge like end-to-end network or whatever that seems to be like the solution some years ago, now it's maybe less used, and people are starting to put more priors, can be demonstrations or structure in the information that we use, such as action or whatever.
Yeah, I mean, I think any solution we have is going to have, any solution we get is going to have a lot of prior. So no, I absolutely agree with that. Obviously, you know, it's about, well, what kind of a prior are we talking about? I guess the reason why I favor end-to-end approaches right now is because I like the idea of closing an objective function associated with a task around all the various components, including perception and grasp planning and so on. But, you know, I'm probably one end of the spectrum here.
Yeah, I was thinking, oh, sorry.
Go ahead.
No, then I will leave other people talking. I was thinking so if you're focusing on like single tasks, I completely agree with you. And I think that also like a lot of recent papers have shown that you can really, like, if you focus a lot on one specific task, especially using maybe end-to-end approaches, you can easily, you can solve it, and even with very good performance. The point is that if we want at some point to have something which is really, really general, so actually end-to-end approaches are supposed to provide generality, but I think it's also pretty hard to have like a single network or a single data set that can be useful like for all the possible grasps in a lot of different scenarios. While instead, if you have maybe some more structure, some kind of different level of abstractions or whatever, it's maybe easier to generalize, because usually models, even if they are learned models, can generalize better than like just a huge like policy or whatever.
Yeah, so I think I absolutely agree with that. So there's, I think there's a, there's definitely a chunk of people out there in the machine learning community who are working on the general AI problem. Build a single system that can solve all the problems. For the most part, I mean, at least in, an application-oriented area like robotic grasping, robotic manipulation, I think that's not what we're about. It's still, I think we still want to use the tools, end-to-end learning, reinforcement learning, imitation learning, perception, whatever, whatever kind of learning we think is appropriate. But but I think we take the new tools and we try to solve the manipulation problems that we've kind of always been trying to solve.
Yeah, that's just absolutely a good viewpoint. And so that's why at this point, like the success rate and dealing with failures is super important, because we want to use these tools to have like useful and practical applications, which of course needs also to be like reliable. Okay, sorry, maybe I biased too much this roundtable.
Well, I guess, but that brings a good topic that we spoke about earlier, which is I think the first question should have been like, what's failure? Like, is it completing a task? Is it being stable in the hand? Is it being repeatable? Is it like a statistical measurement? Does anyone want to say something about that?
I kind of have a hunch that's going to be different for all of us based on what we're trying to do. Like for us, even if we missed a grasp on a handrail, as long as we kept the back foot locked, we could still retry that grasp. So was that actually a failure, or was it just needing to replan? So I think there's a distinction that needs to be made between recoverable and unrecoverable failures. And looking at how to define those is one of the things we're working on.
That's a great point. That's a great point, and that's also so much dependent on context, right?
Yeah, I mean, if you think about a surgical robot that has to grasp something inside your body, of course, in that case, you cannot have different attempts. But in other scenarios, of course, imagine having a robot like just go in your house. I mean, can also try to do things maybe a couple of times. Shouldn't be like super dangerous.
Yeah, one thing I think that we would like to do is develop better methods of automatically learning from failures. I mean, obviously that's one of the attractions of like end-to-end learning or reinforcement learning, is that instead of having a person figure out the failure modes and correct them, then ideally the machine does that. Now, obviously it's not that's not solving all our problems yet, but that seems to be a direction that I don't know. I guess this workshop has inspired me to think about. I mean, what we failure modes are obviously important. What we don't want is to have some engineer who's forever doomed to searching out grasp or manipulation failure modes and correcting them. So yeah, automatically handling that somehow.
Yeah, absolutely. And as humans, we learn mostly from failure. I mean, I don't know, maybe. Massimo wants to. Do I need to? Yeah.
Hi. Yes, this
can talk now.
This is Maximo again. So I fully agree with this point. I think on one hand, failure, the definition of failure depends strongly on the application. But I personally like to see this as a system perspective. probably for emptying the bin, for instance, it's not so important that we have to retry 3 times as long as we actually get the product out. So maybe this is a feasible definition for what I think Andrew was calling recoverable failures. So from the system perspective, maybe we cannot classify that as a failure, but it's just we need a workaround to overcome a difficult situation. The other thing that I wanted to comment on was a point that Robert just mentioned. I think one of the difficult parts for the error recovery is that most of the times we hand code the error recovery strategies, and we just create programs that have multiple alternatives that the robot can choose depending on the current state. But that has the limit that you need some expert knowledge first to define those alternatives. And second, you need to have a system that can decide among those multiple situations, so some sort of situation awareness method. But the problem is that the limit is the expert knowledge of the human. For sure, there will be situations that you have not foreseen on your code. You have to recover from them. And that's, I think, one aspect where I totally see learning approaches being very useful from a system perspective. How do you learn to recover from unexpected failures in a meaningful way?
Especially because I guess almost by definition, these are rare or should be rare occasions. So that how much data can you collect on a learning framework if you're just collecting for very rare?
Yes, exactly. So quoting some famous speaker, dealing with the known knowns is easy. With the known unknowns is also relatively affordable. With the known unknowns, that would be really hard.
Exactly.
Can I say something here? In my opinion on failures, working mainly with prototypes for a few years. And for me, it seems like, you know, a real failure, and it happens a lot. Usually it's like when an encoder breaks, when and then you have, you know, your arm basically jumping and destroying the environment or the robot itself, or you know, you break some, you have a hand and you break some tendons and or you know some motors thereof, and you know there, you know, we could start thinking about failures as an outcome of, you know, hardware failures in the end, and not really software failures, because as you said, like with you know, with grasping itself, I guess it may be a failure that you grasp once and then, you know, maybe you don't succeed and then you retry, but you know, after a day you have done everything. But with hardware failures, I mean, it's the story is a little bit different, and because it may, you may need to follow a different direction into resolving the task. So for me, and this is, I think, like Massimo already spoke about this in his poster presentation, that, you know, it's something that in the labs it happens a lot, and you know, we always have the engineers coming back and fixing the index finger to be able to grasp, even though you could use the rest to do the grasping. So for me, that this is another type of grasping, and you know, there I think learning could play a big role into how to adapt your actions based on your hardware capabilities. I don't know.
Yeah, I think in general, maybe one of the main takeaways of today is like, it seems that for everyone, whatever the reason of the failure is actually the main cause is just this lack of feedback. So when you're able to have some kind of feedback and to react to any possible failure, that's where you have like good performance. When you do not close completely the loop in any possible way, that's where the failures actually increase a lot, and it's really hard. It's harder to get good performance.
So let me just raise maybe the last point, maybe, for instance, before keep with the schedule. But another thing that was more or less discussed now in terms of we almost now are at the point where we say that grasping rigid objects is a solved problem, almost. But for soft objects, that's not even nearly the case. Do you have experience with, let's say, Professor Arada, for example? You for sure have experience with the grasping soft objects. What are the challenges there, really?
Okay, and I have experience on grasping soft object, but the problem is that there are a lot of problems. For example, if we want to grasp Japanese food tofu, it's very slippy, and we have to avoid the slippage between the finger and the object. And also, the object is sometimes fragile. We shouldn't break the object. And also, I have experience on picking up Japanese food sashimi. So in this case, we have to also carefully construct a gripper that can safely grasp the object. So I think that to grasp a soft object, I think that there are many different research topics which have been researched for the rigid object.
Absolutely, like even vision, right? How do you track something that keeps on changing?
Yes, and yeah, we have to track the change of the object configuration according to the elastic displacement. This is definitely one of the research topics. Okay.
Another thing that is still not solved, even for objects that are not deformable, is objects that are transparent or semi-transparent. These days we rely a lot on depth cameras that completely fail when you have such objects. I don't know how to solve that, because if you cannot see an object, then it might be difficult. Maybe with tactile feedback.
But it's so easy for us, right? So easy for us. Like we have something that's made of glass. I mean, all of you can see what I'm holding, right? Even though it's transparent, you can see you can understand the shape of it, just how it reflects.
Right.
And yet so difficult for robots.
I think there is some work there. I mean, I remember from, I think I've seen it from Kostas Danilidis from UPenn, that they were doing basically to see, they were trying to see like how a glass could appear in the you know, the reflections and everything. So but it's a challenging problem indeed, but maybe different type of sensors, Lorenzo, they might be needed for solving this kind of question. To me, it seems that, you know, RGB camera, RGB, not depth cameras, could have an initial estimation of a glass or something like this, and then I'm not sure.
Yeah, I agree.
I don't know. I think we're at a point where you can render these things very well, right? So you can have like synthetic images of something that is made of glass, and use that for learning. Does anybody want to bring in a final subject or conversation? Or
so basically, I guess we're talking here about grasping objects, but when it comes to then do something with the objects, when it comes to manipulate them or to perform a task with it, do you consider that? I mean, that's certainly not a solved problem, but what do you consider are the most immediate issues that we find there? Because in our case, we've seen that, for example, let's say exerting the forces that you want on an object, not only from the control point of view of, for example, a multi-fingered hand, but also taking into account the right friction or taking the feedback, like if your actions on the object are having the desired effect and correct for that, that's really challenging, even with a human in the loop.
Absolutely, and also when you're using a tool, in principle, you're going to be using that tool to interact with the world, right? To have forces between the tool and that you have to account for. So you need to have a grasp that is able to also resist these forces that you're coming out from the. Maybe do you want to, Lorenzo? I know you. I think you've done quite a bit about using tools, humanoid.
Yeah, we did some work on that, but it was very difficult to measure. What is very challenging in this sense is to understand the effect of your actions, how to even define the goal and how to define the success. Suppose you want to unscrew, to open a screw and unscrew it, how to define that you have success, or even opening a drawer. It might be easier, but it's also very difficult to understand when you succeed. So yeah, in tool use, my main concern. In fact, what we did in the past was mostly pushing objects, things where there was a clear way of measuring success or direction of pushing an object. It was much more difficult than to do more complex tasks.
Yeah, I guess I just wanted to mention that the only, I think it was said earlier that, rigid body grasping is, we're doing pretty well there. But I think it all depends on like your perspective on what the problem is. I mean, if the only thing you want to do is just pick up a rigid body object, then we're doing pretty well. But it's never the case that that's the only thing we're trying to do. We're always trying to do some, do some work, perform some task. So I think I think it's just the way our field thinks about. We divide up the problems so that we have rigid body grasping, which we think we're doing pretty well on, and we can feel good about that. But really, we want to get that in itself. There's not a huge amount of value there unless you can attach it to some task, and that's where that's where we often fall short.
Rob, do you think that a manipulation failure, so by manipulation I mean doing something meaningful with an object or a tool, is a result of failure in grasp, whatever definition you give to this failure, is an outcome, or you may have successful grasps and then fail in the manipulation task? Do you think these are connected?
I didn't quite get what you're saying. Say that again.
I mean, does it in the end, the grasping on how you grasp an object defines if you will be successful in manipulating something with this object, or doing something meaningful with this object?
I mean, I guess I'm advocating that you reason about your grasp at the time you're doing the task, so that you can figure out how you want to grasp it.
All right. So you really think that the way that you grasp something defines if the manipulation task will be successful. Anyhow, okay.
I mean I think that they're pretty tightly related. So for example, in tool manipulation, obviously you have to hold the tool correctly in order to use it. But in most tasks that we're most of the time when we're trying to solve some task, even if it's block stacking, we have to hold the blocks in the right way in order to be able to place them, so as to achieve some structure. I mean, it's rare that it doesn't matter how you grasp.
All right.
Shall we call it then?
I mean, if anybody has to raise any other question, I don't know is there anything on the chat? But no, okay, there is nothing. Is there somebody that would like to ask anything else and for today from the invited speakers? from the organizers?
No, apparently not.
All right. I guess, Joao, yes, we could.
Let's wrap it. And just invite everyone to come back. We'll be doing the second part of this tomorrow. It's midnight UTC, so whatever time that is in your time zone.
It is midnight of Wednesday, Joao, right? So it is, I think.
Yeah.
It's rather
not,
complicated with the change of time. So we
yeah,
had it was a mess basically to understand what time zone.
Yeah, I learned that not every country changes the time at the same time. Yeah. So it's midnight UTC, just to check what it is in your place.
Okay.
We'll have Jeanette Bog, Ken Goldberg, Dieter Fox, and Juxi Leitner. And then another live session like this with questions, some other 5 people who contributions, slides. Thank you very much for coming. Thank you very, very much to the speakers who took the time to present their work to us. We'll see you soon.
And all the attendees, right? 27 people, roughly.
Yeah. Thanks also to the contributors.
Thank you very much.
And also to Joao Academic. You made really a huge work to organize everything, all this. So you made it also to Dimitri, to everyone.
All right, guys. It was
Thank
good
you.
to see you all. Let's stop recording, by the way, Joao.
Yes.